Fundamental Organometallic Chemistry, Chemistry 4105 for the students of Master 1 Chemistry. The objective of this course, this is an advanced undergraduate course, and in this course we want to study how metal is bound to a ligand, because the type of the metal-ligand bond is different from that, for example, carbon-carbon, or as usual in organic chemistry. We will study the type of this bond Ml. We have two types, sigma bond or pi bond, and in the family of M sigma bonds, we will study M ligand Lewis base, oxygen, sulfur, nitrogen, and M carbonyl CO, then M phosphine, M alkyl, and M hydride. This is the most important Ml ligands sigma bond. In other parts, we pass to another type of Ml bond, which is the M pi bond ligand, and we will study the metal alkene, the metal alkyne. Then we pass to the bond M double bond ligand, which is the metal carbene, and M triple bond ligand, the metal carbide. In the second part, we will study the most important reactions known in organometallic chemistry, and we have about 13 reactions. These reactions, the most important is, for example, in part B, the ligand substitution, then the oxidative addition reductive elimination, the migratory insertion, the hydride elimination. Then we pass to the nucleophilic and electrophilic attack on some coordinating ligands. The fruit of this course is to know or to construct the catalytic cycle and to know the mechanism. And the fruit of this course, you have a reaction A plus B in the presence of catalyst, transition metal catalyst, homogeneous or heterogeneous, that gives C plus D. We have to propose a convenient mechanism. Why we say we have to propose a convenient mechanism? Because we are not sure about the mechanism. We can prove if a mechanism is not correct if in one of its steps, but we could never prove that this is really the mechanism of the reaction, since we have to pass to lab to have some indications about reaction, about the product formed, about the intermediates, then to write the catalytic cycle. We'll start chapter 1, the fundamentals and the notations important to explain and understand the bond metal ligand. First of all, what is the difference between coordination complex or organometallic complex? In the coordination complex, we have a metal that coordinates to a ligand according to a coordinate covalent bond. But in organometallic complex, we have at least one bond M carbon. And as you know, the bond, for example, between M amine is different from that between M alkyl. M amine is a coordination complex, and M alkyl is an organometallic complex. But in books, in organic books and organometallic books, they don't make the difference between coordination complex and organometallic complex, and they use, for example, organometallic notation. In our course, we will use the term organometallic complex. If I take, for example, this complex, I have a metal center that is bound to oxygen ligands. So this is a coordination. In this complex, we have ruthenium bound to nitrogen, and ruthenium is bound to cyclopentadienyl. So we have MC bond, and this is organometallic. In this complex, palladium tetraphenylphosphine, this is, by theory, a coordination complex. But we use the notation this is an organometallic complex. Okay, so we'll not make the difference between coordination and organometallic, and we will use the term organometallic. Organometallic complex contains at least one metal carbon bond. The type of bonds MC can be M single bond C, like in this complex of ruthenium, we have ruthenium single bond C, and we have also ruthenium that is bound to benzene, to 6 carbon of benzene, so the bond is hapto-6 and will be explained later the hapticity. The bond can be also metal double bond carbon. In this complex, we have platinum bound to 2 carbon atoms. To note that the bond M, the bond platinum, C double bond C by this way is different than platinum C double bond C by this way. In the first example, the donation of electrons from the carbon is done from the hybrid orbitals of the carbon. And in the second, the bond between platinum and alkene is due to the breaking of the p bonds of the 2 carbon that form the pi bond. So the type of connection between metal and the ligand, metal carbon ligand, is very important to know what is the site of binding. The bond can be also metal alkyne, where the metal is bound to 2 carbon atoms. The most familiar ligands we will study are CO, the carbon monoxide, which is responsible for the carbonylation reaction. Suppose in organic synthesis, we want to add carbonyl group. In organometallic chemistry, we can join this carbonyl to a metal complex, then doing some internal reactions on the ligands around the metal, and by this way we can introduce a ligand, a carbonyl group CO. The second important ligands are alkenes, and alkenes are very important in organometallic chemistry because when binding to metal M, we can attack this alkene by hydrogen present on M, which is the metal hydride, and by this way we transform the alkene to alkane. Other important ligands like alkynes, arenes, or alkyl also will be studied in details, and we have the halogens and phosphine. Phosphine is one of the most important ligands that can be bound to a metal center because metal phosphine is a bond that can be broken easily if the phosphine is bulky. For example, in organic synthesis, we use triflate as a good living group. In organometallic chemistry, we use phosphine as a good living group. Organometallic complex can contain the same or different types of ligands. The application of organometallic complexes. They were used as catalysts, and we have the famous reaction of Wilkinson, which is the hydrogenation of cyclohexene to cyclohexane, and Wilkinson won the Nobel Prize in 1973. Wilkinson is a British scientist. Organometallic complexes were used also as drugs, as medicinal drugs. We have an example about the arsenophenamine, where we have arsenic metal center and phenamine ligand, known as Salvarin 1910, which was used for the treatment of syphilis in 1940. The principal application of the organometallic complex is its use as a catalyst in the organic synthesis reaction. One of the most important steps in organometallic chemistry is to know if this complex can be used as a catalyst or not. And if it can be used as a catalyst, what is the mechanism of catalysis? So one of the most important application of the organometallic complexes is to know if they can be used as a catalyst or not. The first step is to calculate the number of electrons in this metal complex. Suppose, for example, we have a complex M, L1, L2, L3, L4. To count the electrons in this metal complex, we have to know the electrons provided by M. M is a transition metal, so it has electrons D, and the nature of the ligands around the metal center L1, L2, L3, L4. If we know the nature of these ligands, we can predict the number of electrons donating by this ligand to the metal M. How to know the number of electrons donating by a ligand? Suppose we have CH3CN. If we draw the structure, Lewis structure, CH3, CN, N. The structure is complete. The central atom has 8 electrons, and the outer atom have also 8 electrons. So the Lewis structure is complete. We don't need to add electrons to this structure. CH3CN is a neutral ligand and 2 electron donor from the lone pair of N. Pay attention. The charge of the ligand is different from the donation of the ligand. Suppose you have another ligand, L2 is Cl. We don't know the donation of this ligand. I can write Lewis structure. The Lewis structure Cl has 7 electrons. To have complete Lewis structure, we have to add 1 electron. So Cl used is Cl minus. the charge is 1 minus and Cl minus is 2 electron donor. We can write the structure by this way. So it's 2 electron donor by 1 lone pair. By theory, we have possibility of 4 electron donor by 2 lone pairs or 6 electron donor by 3 lone pairs. And we will see after, when writing the ligands, we can know if this ligand is 2, 4, or 6 electron donor. The simplest is to be 2 electron donor. And we have some cases the ligand is 4 electron donor, and the rare case for the ligand is to be 6 electron donor, because it depends on the geometry of the ligand. Cl minus is 2 electron donor. After we write Lewis structure of the ligands L1, L2, L3, L4, we can know the charge and the donation. And I repeat, the charge of the ligand is different from the donation. When we know the charge, the importance of the charge of the ligand, we can calculate the oxidation state of M. Why the oxidation state is so important? As I said, we have M found in this structure. We don't know if it's M0 or M1 or M2 or M3. It depends on the charge of the ligands around. Suppose L3 is in neutral, L4 is in neutral, L1 is 1 minus, L2 is double minus. So in this case, the oxidation state of M is X plus 0 charge of the first ligand plus 0 of the second ligand plus 1 minus of the third plus 2 minus of the fourth equal 0. The sum of the oxidation state is equal to 0. In this case, M is M oxidation state 3. X minus 1 minus 2 equals 0, so X equals 3. And if M is S2 D6, that we write D8. So M2, this is for M0. So M3 is D5, implies around M we have 5 electrons. 5 electrons from M, and we count the donation of each ligand. We can calculate the total number of electrons in this complex. So some other important notations in order to calculate the total number of electrons in a complex, and I repeat, the total number of electrons around a complex or in a complex give us indication if it can be used as catalyst or not. Electropositive and electronegative. Where do the partial positive and negative charge in a molecule reside? This is important to determine how much electron density will be donating from a ligand to a metal center, and where a nucleophile or electrophile will likely attack for chemical reaction. To explain, we return to the example before. It's M-acetonitrile. M-acetonitrile, in the acetonitrile ligand CH3CN, the total valence electrons are distributed between these atoms. But the nitrogen is the site of binding. Why? Because we have lone pair. So in this example, acetonitrile is neutral and is 2 electron donor, and we don't have a problem to find the site of donation because we have the lone pair on N. But suppose, for example, we have a CO ligand, carbonyl. If we write the Lewis structure of carbonyl, we will find a lone pair on carbon and a lone pair on oxygen. So the CO ligand has two sites of binding to a metal center, from the lone pair of C or from the lone pair of O. But since oxygen is more electronegative than carbon, so it would not give its lone pair to a metal center, so the donation from the CO ligand to the metal center is from the lone pair of the carbon atom. So this is an example that shows the importance to know the electronegativity of the binding atoms that may attack or that may donate the metal center. The importance of the Lewis structure, I repeat, if you don't know, for example, the charge and the donation of the ligand, you can write Lewis structure. And Lewis structure, if you need electrons to have saturated Lewis structure, so you add 1 electron, this ligand is 1 minus. You have to add 2 electrons, this ligand is 2 minus. And from the Lewis structure, we can know the site of binding in the structure, and we can know also the donation of electrons. And I repeat, we have difference between the charge of the ligand and the donation of the ligand. The oxidation state is very important to know the number of electrons around metal center, and the oxidation state can be found if you know the charge of the ligands around M. To note that if the complex is neutral, the sum of the oxidation state of all components, the metal center and the ligands, is equal to 0. If the charge of the ligand is 1 minus, for example, the sum of the oxidation state is equal to -1. And if the charge is equal, the charge of the complex is equal +1, the sum of the oxidation state is equal +1. Organic line notation, we prefer in organic chemistry to write the CH bond as a line, because we pass to complexes which are hexa-coordinated. So to draw the structure, it's easier to represent the CH bond by a line. The electron density is different from the donation, and this is the common mistake in organometallic chemistry, is when we say the electron density is the donation is the electronegativity. Never confuse between these terms. Consider a bond Ml. The charge of the ligand L may be 1 minus, 2 minus, 3 minus, or more. It depends on the nature of this ligand. And how to know the charge of the ligand? By writing Lewis structure. Suppose the ligand is 2 electron donor, or 4 electron donor, or 6 electron donor. This is different from the charge, and this donation is the capacity of donation. How to know the donation of a ligand? When we write the Lewis structure, from the active sites in the structure, we can know the number of electrons that may be donating by this ligand. So the charge is different from the capacity of donation. If the ligand is 2-electron donor, we ask that question now, how these 2 electrons are transferred to the metal M. If these 2 electrons are transferred close to the metal M, so the electron density around M is great, and we say that this metal center is rich in electron density. And if these 2 electrons are donating from the ligand and are not close to the metal M, are close to the ligand, so the electron density around M is low, and we say that this metal is poor in electron density. So the charge of the ligand and the donation of the ligand and the electron density around metal center are 3 different terms, but there are relations between them. The electron density example, what are the ligands supposed to give high electron density to the metal M? If the binding site of the ligand is not highly electronegative, this is from the site of the ligand. To note that the electron density around the metal M depends on the nature of M and on the nature of L. If M is rich in d electrons, this may increase the electron density around M. And if the ligand is donor of electron and the site of binding is not electronegative, so it will give its high capacity of electrons to the metal M, and in this case, the metal M is rich in electrons. So the responsibility is for the nature of M and the nature of L. Suppose the metal center is rich in electron and the ligand is poor donor, is donor of 2 electrons, but these 2 electrons are not completely transferred to the region of the metal center. In this case, we have to make a balance to know if the metal center is rich in electron, but in general, we say that the electron density is low. When is the metal center rich in electrons? I will quote the factors in order of importance. The metal center is rich in electrons when 1. The complex is anionic, so the complex is charged negatively. 2. When the ligand around M are good donor. What is the meaning of good donor? The ligand contains a site of binding of low electronegativity. When if the electron is poor, when is the metal center poor in electron density. I will also quote in the order of importance. 1. When the complex is cationic. The complex cationic means poor in electron density. 2. When the ligands L around the metal center are poor donor. To note that the ligand may be donor or acceptor. When the ligand is poor donor, that means it's a good acceptor, and I will explain later between the concept, the difference between the concept of donation and acceptance. And the ligand is poor donor, what in general contain a binding site or an atom of high electronegativity. We will have some examples about the donation of ligands. Consider, for example, the fluoride anion F minus. F minus has a charge 1 minus and is 2 electron donor. 1 minus, that means 2 electron donor. But F minus is not a good ligand, is a poor donor ligand to a metal M, and this is due to the high electronegativity of F. F minus is poor donor to metal M, so the bond MF is the less stable. And what is the meaning of a bond less stable? So if you have an organometallic complex, you have a bond MF, that means the bond is unstable and M can release easily the fluoride F minus. Consider the methyl anion CH3 minus. CH3 minus is a very good donor, and the electron richness comes from the lower electronegativity of carbon. P-methyl-3 is a good sigma donor. PO-methyl-3 is a poor sigma donor, is a poor donor. Phosphorus does not have high electronegativity. So by theory, phosphorus can give its lone pair to any ligand, to any metal center. Methyl group is a good donor group. So it will increase the electron density around P, and in this case, P will donate the maximum of its capacity to the metal M, so P-methyl-3 is a good donor ligand. Consider PO-methyl-3. As I said, by theory, P is good donor of the lone pair since its electronegativity is low. But the presence of oxygen near P, oxygen will pump the electron density of phosphorus to itself. So in this case, the phosphorus is not a good donor.